I guess it's related to linear programming or integer programming. And we are talking about just the integers or the positive integers here, the natural numbers. That scripted in just means the positive integers. 1, 2, 3. Sometimes the natural numbers include 0. Some people, they let it include 0, but not the case with the way I did, my preference. Okay, so we are dealing with natural numbers. Now we have what we have here is a equality constraint. Now the b sub i's are all natural numbers, and this is burning on both ends. Little n is the count, okay, and then all the b sub i's themselves are natural numbers, okay? Now this is a lot of discovering going on down here in this table, nothing too rigorous. We're looking for a way to choose the count of the summands and the type of summands to maximize the product right here, okay? And this observation ends up being pretty clear if you just look. The ones screw everything up because they're not doing anything in terms of maximizing the product. And hopefully this example here, 14 is just considered the trivial product, so no big deal there. N is equal to 1. Now for 5 summands here, if you try a larger number, n, you see that squeezes you down on your other choices, and you only get small products like this, okay? Now again, folks, hopefully the table's good enough to convince you. Right here, I just went from 9, and I just changed 9 to 3 plus 3 plus 3. And look what happened there. It shows you the problem with choosing, quote, large numbers, because 3 plus 3 plus 3 gives you this contribution of 3 cubed in the product. Okay, notice I'm leaving the ones out here. I'm leaving the ones out, which just enforces the validity of this statement right here. You wouldn't even dream of putting ones in these things, okay? Now, you just keep playing around with the numbers and notice the patterns. I don't even remember what I did right here. Maybe I switched it from 7 to 6, and we have 3 3s again. So we have 3 cubed times 2 squared is 108, which is bigger than this number, okay? Now it turns out this is the biggest one, and this is the answer to the question right here. Okay, this circle piece right here is the answer to the question, 162. Now I know I'm not presenting you with any rigor, but I think it's fairly convincing if you just look at some of the patterns here. Like notice that, for example, there's a 4 right here. See how things change? Fours will be excluded from the b sub i's just because of this statement right here. Notice that we have 108 and 108 right here, right? So I simply replace 2 squared with 4, and we see that you can always do that, right? So 4 would never, in other words, 4 would never be 4 can never be equal to a b sub I. Okay, not equal to a b sub I. And similar statements for larger numbers are going to happen, folks. So 4 would never equal to a b sub I simply because it's equal to 2 squared. All right, and y'all, that is supposed to be a not equal sign, a negated relation there. All right, now, and the rest of this, folks, again, is just discovery. Notice I tried a 5 here, and you still have a smaller number than 162. Okay, so nothing sophisticated by any stretch of the imagination right here. But it turns out there's nothing special about 14 here. Your answer will always be combinations of 3 and 2 in this exponential form. And it's kind of an amazing discovery. Now, again, not rigorous, but look what happened when I tried bigger numbers here. You get smaller products. Right down here it was fairly close. 2 to the 4th times 3 squared gives you 144. But that, again, that's less than the 162, which is the answer to this question. Now, I do want to write down an observation. It's a simple observation, but 3 squared 3 squared is certainly greater than 2 cubed. Isn't that crazy? But something that simple, I think, is kind of at the bottom of all of this, believe it or not. Okay? See, 3 squared gives you 9. This gives you 8. But this is 3 2's in the product, right? This is only 2 3's in the product. So again, I think this is everything right here almost, I mean, I don't think there's much else to say, 9 is greater than 8, right? This would give you only 2 3s in the product, all right? And this would give you 3 2s in the product, and yet this is a bigger number, right? Now notice the same thing is not true. Let's just as a contrast here, just to see why these 3s and 2s are kind of special. Notice that 4 squared, okay, 4 squared is not greater. Again, I like using these negated relations. They're nice, man. 4 squared is not greater than 3 cubed. It's kind of you're just bumping it up. Whoops. That's 3 cubed right there. Okay. So again, you have 3 is bigger than 2. 3 squared is greater than 2 cubed. Okay. 4 is bigger than 3, but 4 squared is just 16. 3 cubed is 27, right? So you see, it's kind of a break point, whatever. This is some kind of magical thing here with the 3s and the 2s, you know. Now let's go ahead and take a look at just a concrete example here. I could just tell you guys to do this if you want to, if I was a teacher. All right, but you see, you can notice that you can write 1,000. Okay, you can write 1,000 equals. Okay, what do we have here? Equals to. If you divide this down and then keep the idea of the 3s and the 2s, you could write this as 996. Right, 996 plus 4. I'm trying to work with this trackpad because the screen always moves if I use the mouse. All right, so, but notice what this does for us right here. You see, this would give rise to a product. See, this is 996, but that's 332 times 3, right? So this is 332. 332 times 3. And of course, folks, you could write this as 2 plus 2, right? So that would give you your one, let me write this down, 2 plus 2. All right. So notice, y'all, in this case, your n would actually be 334. Your little n would be 334. All right, but notice that based on the so-called reasoning and discovery we did on the previous page here, that would tell us this would max out at what? 332, or 3 raised to the 332. That would be 3 raised to the 332nd power. Y'all, that's a 332 right there, times 2 squared. Okay. And that's it. I mean, this is I just think it's neat. It's all about 3s and 2s here. We've seen that a 4 doesn't work because it can replace with 2 squared, and also 3 squared is greater than 2 cubed. That's really what this all seems to boil down to. So this would be the answer for this problem, folks. And again, I hope that's legible. 3 raised to the 332 power based on this analysis here. And again, this is just a way of writing all of this out nicely. Obviously, you don't want to write down 3 plus 3 plus 3 332 times. So your little n would be 334 sum n's over here. Literally 3 plus 3 plus 3, 332 times. And then 2 plus 2 adds up to 1,000. And then based on the analysis earlier, you raise 3 to that power and 2 to the second power. Okay. So that does it, folks. I thought that's super cool. So anytime you have something like this, the maximization is always going to be 3 raised to some power and 2 raised to a power not higher than 2. Okay. And again, just since I have you guys, your captive attention here, notice you might be tempted to say, well, why not just do 3 raised to the 333, right? You're going, that wouldn't that be, but notice your other summand would just be 1. Okay, that's if we did 3 raised to the 333. Okay. Okay, you would have plus 1, right? And we've seen that 1s are anathema, when you're doing something like this. Okay, so you see how this number right here is definitely a smaller number when you multiply against 1. 3 raised to the 333 is a smaller number than this, right? Because this is 4, right? This number is 4, and that's clearly larger than 3, blah, blah. So this is larger than this. It's tempting to try this, okay? But this is the correct answer. And you can do this with anything. It's about dividing by 3 and playing a little bit of a game with the 2's. But anyway, I hope you enjoyed. I like that one quite a bit.